All right, settle in, because I want to tell you a story. A story about dreams, ambition, and reaching for the stars, quite literally. Imagine it's night. You're outside, maybe in your backyard, maybe out in the countryside where the city lights don't drown out the heavens. You look up. The vast expanse of space stretches above you, a canvas of black velvet sprinkled with diamonds. And you think, like I often do, space, it's just there. So close, yet so impossibly far. For most of us, space remains a distant dream. We see the breathtaking images from telescopes, the stunning documentaries, the occasional rocket launch lighting up the news. We marvel at astronauts floating weightlessly, gazing back at our blue marble, Earth. But for us, ordinary folks, getting up there? That's something for heroes in white suits or billionaires with more money than sense. It's hard to get to space. Really, really hard. And expensive. Astronomically expensive, you might say. We've all wished, at some point, haven't we? Wished for an easy, affordable way to just pop up there. To see our planet hanging in the void, a vibrant jewel against the infinite darkness. To experience that overview effect, that shift in perspective that astronauts talk about, that feeling of unity and fragility of our home. But right now, the reality is stark. Your ticket to that view is either years of rigorous training and dedication to become an astronaut, or, well, being incredibly, ridiculously wealthy. Neither option is exactly within reach for the average person. But what if I told you there's a concept, a wild idea, that could change everything? An idea that could potentially make space accessible, not just for the elite, but for anyone who dreams of touching the stars. An idea that could be the very launch pad for humanity's grand adventure into the universe? I'm talking about the space elevator. Sounds like science fiction, right? Straight out of a futuristic movie. And in many ways, it still is. But the concept is surprisingly grounded in real science, real physics. So, how does this fantastical sounding thing actually work? To understand that, we need to take a step back and think about orbits. Imagine you're throwing a ball. On Earth, you toss it, it arcs through the air, and thud, it hits the ground. Gravity pulls it down, of course. Now, imagine you're in space. Gravity still works, but it works differently. Being in orbit, essentially, is just a fancy way of saying you're constantly falling towards something, like the Earth, but you're moving sideways just fast enough to keep missing it. Think of it this way. If you throw that ball sideways, and you throw it really, really hard, the Earth is curved, right? Well, if you throw it sideways at just the right speed, the curvature of the Earth makes the ground fall away beneath the ball as fast as gravity pulls it down. So, instead of hitting the ground, it just keeps going, circling the Earth in orbit. That's how rockets get into orbit. They don't just go straight up. They go up, and then they tilt sideways and accelerate, 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 until they're moving sideways fast enough to essentially fall around the Earth. It takes a lot of energy to do that, a tremendous amount of fuel to get that sideways speed. But a space elevator? It's different. It's ingenious, really. It taps into the energy of Earth's own rotation. Think of it like this. Imagine a child spinning a toy airplane on a string. The child's hand is the Earth, spinning around. The airplane at the end of the string, that's our cargo, heading to space. Now, picture a tiny ant clinging to the child's hand, right where the string is held. As the child spins, and the ant starts to climb out along the string, what happens? It starts to move faster and faster, further and further out, propelled by the spinning motion. That's the basic idea of a space elevator. Instead of rockets blasting off, burning tons of fuel, we'd have an elevator, a tether stretching from the Earth's surface all the way into space. And instead of needing massive sideways acceleration, the sideways motion comes for free, thanks to the Earth spinning beneath us. We just need to provide the energy to go up. Now, imagine this elevator in reality. It's not just a rope dangling in the sky, of course. A space elevator has 4 key parts. First, there's the tether itself. This is the elevator cable, the super strong ribbon extending from Earth to space. Then, there's the anchor, firmly planted on Earth, perhaps out in the ocean, providing the base for the tether. At the very top, far out in space, is the counterweight. This is crucial. It's what keeps the tether taut and prevents it from collapsing. And finally, the climber. This is our elevator car, the vehicle that travels up and down the tether, carrying cargo, and maybe even people into space. Think about the benefits. Compared to rockets, launching cargo with a space elevator would be dramatically cheaper. Rockets are incredibly inefficient. Most of their weight is fuel, just to get a tiny payload into orbit. Current rocket launches cost around $20,000 per kilogram of payload. Imagine the cost of sending a human, let alone a car, or the entire International Space Station. But a space elevator, imagine the cost plummeting, potentially 100-fold, down to just a few $100s per kilogram. Suddenly, space isn't just for governments and billionaires anymore. It's within reach. Think about the possibilities. Space tourism becomes a real industry. Building space stations, lunar bases, even missions to Mars becomes vastly more affordable. The exploration of the universe, truly, begins to open up. But, and there's always a but, building a space elevator is, well, it's monumentally challenging. The biggest hurdle? That tether. It needs to be unlike anything we've ever created. It needs to be incredibly strong, light, affordable, and resilient. Stronger than steel, lighter than feathers, and able to withstand the harsh conditions of space. Atmospheric corrosion, radiation, micrometeorite impacts, space debris. We're talking about materials that, frankly, we don't yet have. We have promising candidates, materials like graphene and diamond nanothreads, incredibly strong materials at the nanoscale. But even these might not be strong enough, not yet. And it's not just strength. Imagine climbing this elevator. It's not a quick trip. It would take days to ascend to geostationary orbit and beyond. How do you power the climber? Do you need a nuclear reactor on board? Or do we beam power from the ground with a super powerful laser, shooting energy through the atmosphere to power the elevator car? And then there's the sheer scale of it. We're talking about a tether potentially 36,000 kilometers long. Where do you even get the raw materials to build something that vast? Do you make it on Earth and launch it into space, an incredibly complex undertaking in itself? Or do you try to manufacture it in space, even more complex? Some have even suggested asteroid mining, extracting materials from space rocks to build our space elevator in space. The scale of the engineering and logistics is mind-boggling. And then there's the risk. A space elevator, for all its potential, is inherently vulnerable. Imagine what happens if that tether breaks. It's not just a snapped cable. It's a catastrophic event. If it breaks near the anchor, the immense counterweight in space will whip the remaining tether upwards, potentially destroying the base and anything near it. If it breaks near the counterweight, the tether will fall, a colossal whip crashing down, wrapping around the Earth, and potentially causing untold damage and creating a cloud of dangerous space debris that could threaten all future space activities. It's a do or do not. There is no try kind of project. If we build a space elevator on Earth, we have to get it right the first time. There's no room for error. The stakes are too high. Because of these daunting challenges, some experts have proposed a stepping stone approach. Build a space elevator on the Moon first. The Moon's gravity is much weaker than Earth's, making the tether requirements less extreme. We could potentially use existing materials like Kevlar for a lunar space elevator. It would be a smaller, less risky project, a test bed, a way to learn and develop the technologies needed for an Earth-based elevator. Even with all these hurdles, the potential payoff of a working space elevator is immense. It could be the key that unlocks the door to truly becoming a spacefaring civilization. Maybe we'll never actually build a space elevator on Earth. Maybe the challenges are just too great, too risky, too expensive for even humanity's ambition. But even in trying, in striving for this seemingly impossible dream, we might learn an awful lot. We might develop new materials, new technologies, new ways of thinking about space and our place in the cosmos. And when it comes to exploring the universe, to reaching for the stars, to dreaming of a glorious future among them, well, perhaps there can never be too many dreams, no matter how audacious they may seem. Perhaps the very act of dreaming, of striving for the seemingly impossible, is what truly makes us human and what will ultimately propel us, not just into space, but into a brighter future for all.